Today we're going to look at direction fields, autonomous differential equations, and the methods of isocline. Up at the top here, we've got a website that you're going to use to do your homework in order to sketch direction fields, and I'll show you how to use that in this lecture. So a direction field is a two-dimensional graph that tells you the direction each solution goes in. So your typical well-behaved first-order differential equation is going to have one solution that passes through each point. Well, we don't know what the solution looks like, all right? But we can approximate what the solution looks like by looking at the tangent lines of the solution, because dy dx is the slope of the tangent at any point. So here's how you would make a direction field by hand, which you're not going to want to do. Dy dx is x plus y. So at any point in the plane, x comma y, the slope of a solution passing through that point will be x plus y. So just pick some points at random in the plane. I picked 3 points here. At 1 comma 1, my slope, y prime, is x plus y. So that's 1 plus 1, so that's 2. So I go to the point 1 comma 1 in the plane, and I draw a little lineal element, a little line of slope 2. Then I move on to another point. Let's say when x is 1, y is 2, the slope passing through that point is going to be 1 plus 2, which is 3. So I go to x is 1, y is 2, and I draw a little line of slope 3, which is a little steeper than the one above. Those slopes look a little bit steep to me. It's hard to do this by hand. And then y prime here at 1, negative 1 is going to be 1 plus negative 1, which is 0. So I go to 1, negative 1, draw a little line of slope 0. So if I have a lot of time, I'm going to fill out the whole plane doing that, and then I can get an idea of what solutions will look like. So let's jump ahead to technology, where we've got a direction field filled out. And so looking at this, you can really get an idea of what solutions look like, because solutions, any solution passing through a given point has to be tangent to that line. So as you're drawing solutions, you can't cross lines at like a perpendicular angle because you want to be tangent to that line. All right. So a solution going through negative 1, 3 is going to have to go something like this. And then as it approaches this line here, it won't be able to cross that line because it has to stay tangent. So it's going to just come up like that. A solution through negative 2, 1 is going to look something like that. Just follow the flow. Think of it as current in a river. You just have to go with the flow. All right, and then this solution is going to look something like that. How do I know that there's only one solution that passes through every point? Well, I know it from the last section, which is existence and uniqueness. Remember from the EUT theorem, if a differential equation looks like y prime equals f of xy, and we have an initial point, when do we know we have a solution? When do we know it's unique? Well, one, the function, for us, the function f of xy is x plus y. That's continuous for all x naught, y naught. So that means condition 1 of the EUT is satisfied at every point in the plane. What about condition 2? If you recall, condition 2 requires that the partial with respect to y of f, which in this case would be 1, also has to be continuous in a little rectangle around the point. Well, this is continuous for all xy, so it's certainly continuous in some rectangle around x naught, y naught. So we know we have a unique solution that passes through every point in the plane. So now let me jump to the technology and show you how this works. You don't need the link address. You could just Google Bluffton differential equations and you're going to come up with it. This is what the site looks like. On the first tab, it will say 1 ODE, and that's what you want. And actually, the default equation is x plus y, which is the one we're looking at. But you could change that to y squared, and you can see that the direction field changes. Let me change it back to x plus y. And if you are interested in a larger portion of the plane, you can change up the values on x and y, and you can change the number of line segments. I'll just leave it at the default. And then to plot numerical solutions, you can just click on the plane at any point, and it'll draw a solution through that point. Or to be more precise, if you want to know exactly what a solution looks like through any one given point, let's say 2, 1, you can enter 2 for x, 1 for y, and click on, let me clear all curves, click on submit, and it'll draw a solution passing through that point. All right, so now let's go back to our page. There's a way to speed up drawing a direction field by hand, and that would be by using isoclines. And an isocline is a curve on which the slope of the tangents is constant. So the f of xy part is a constant. So for example, I can look at this same direction field and draw it by hand a little bit quicker than I was doing up here. Here it was just one point at a time. Here I could do it one curve at a time by looking at the isoclines. So for example, I just pick some values of the slope. So for example, if I want to look at all the places on the plane where the slope is 0, then, so that's my f of xy equals 0, then I know y prime is x plus y, so I'm saying x plus y is 0. Well, that's the curve y equals negative x. So that's actually a line. When I go to the line y equals negative x, everywhere on that line I'll draw little lineal elements of slope 0. All right, what about slope 1? If y prime equals 1, then I have x plus y equals 1, so y is 1 minus x. So that's a line, slope negative 1, it goes through y equals positive 1 up here. So along this line, I'm going to draw lines of slope 1. Let's do one with slope negative 1, you're getting the idea. And you're going to fill out the whole plane. You're going to end up with something like this. Now, isoclines have value other than drawing a slope field by hand, because in reality, in 2021, you're not going to be drawing slope fields by hand, but it's good to know what you're looking at. When you look at a slope field, I want you to understand what you're looking at. All right, autonomous first-order differential equations. An autonomous first-order differential equation has a slope that only depends on y. So it looks like dy dx is f of y. So the function f of xy that goes on this side is just f of y, not f of xy. So you can tell a first-order differential autonomous equation by looking at it. If it's of the form y prime equals some function, that function can't have any x's in it. So no, not autonomous. No, not autonomous. Yes, autonomous. So that's how you can identify an autonomous equation by looking at it. How can you identify an autonomous direction field by looking at it? Well, the answer is the isoclines will be horizontal lines because the slopes only depend on y. That means for every x, you have a given y, for every x, the slope will be the same. So this is the direction field of an autonomous differential equation. And these solutions here that correspond to slope 0, those are special solutions. They're called equilibrium solutions, because if you have a solution that's approaching an equilibrium solution, it won't be able to get past that equilibrium solution. So these solutions would go down, and remember, they have to be tangent to all the lines, so you can't cross a horizontal line. So all your solutions are going to approach that equilibrium solution on this side. And then on this side, they're also going to approach that equilibrium solution, hence the name equilibrium solution. All right, so let's take a look at 3 direction fields here. Which ones are autonomous? So just look at horizontal lines. Slopes along those horizontal lines are definitely not constant. So they're going steep and less steep and less steep. So this is a no. What about this guy? If I draw any horizontal line in the plane, it looks like those slopes are constant along all the horizontal lines. So this guy is autonomous, and this guy definitely autonomous. So here is a fun exercise. You're given a few differential equations, in this case 4. Which differential equation could have this slope field shown? So part of this is just going to be by ruling some stuff out. So let's go for the low-hanging fruit. Let's look at this slope field. Is it autonomous? No, because if I look at the horizontal lines, slopes on horizontal lines are not constant. So this is not autonomous. So automatically I can 86 this guy and this guy, because those are both autonomous differential equations. All right, so now we only have 2 left to choose from. So now we're going to have to go do a little bit of sleuthing. Let's take a look at this guy. If x is positive, the slopes are positive. So that works. Over here, whenever x is positive, my slopes are all positive. But when x is negative, when x is negative, the slopes, y prime, are also negative, because a negative cubed is a negative. Well, if I look over here when x is negative, none of these slopes is negative. They're all pointing in the positive direction. So I can count that guy out. So by process of elimination, it's this guy. But let's just do a safety check. When x is negative, y prime is going to be positive. So that works because all these slopes are positive. And then when x is, close to 0, the smaller x is, the smaller the slope is. That works. In fact, the slopes are 0 when x is 0. And then as I move away from the origin, as x gets larger, either in the negative direction or the positive direction, the slopes get more steep. So I feel confident that that's my answer. Okay, another fun example, the logistic equation. Use isoclines, should be an S there, to sketch the direction field of this differential equation, and then we're going to answer some questions based on the direction field. So the first thing you want to do when you're drawing the direction field for an autonomous differential equation is look for the equilibrium solutions. So those are places where the derivative is 0. So dp dt is 0 at, well, this is factored here, p equals 0 and p equals 3. So at p equals 0 and p equals 3, I have lines of slope 0. So let's just draw those in. Got an equilibrium solution here. Notice I'm not drawing this graph for p negative or t negative, because typically the logistic equation is talking about, well, in this case, populations in thousands of a certain species. You can't have negative amounts of species, and you can't have negative time. All right, and then this is p equal 3 for 3,000. Got an equilibrium solution there. And then you just have to figure out what's going on between the equilibrium solutions. So pick a value between 0 and 3. So that's an if. If p is between 0 and 3, dp dt, we don't care what the value is. We just care whether it's positive or negative. So dp dt is going to be, okay, so I'm looking at this, a positive, because if p is between 0 and 3, p is positive. So I'll have a positive times 3 minus p. If p is less than 3 is going to be a positive, so that's going to be positive. So the slopes in here, remember for autonomous, for all t, you'll have the same value of the slope going in a horizontal line. So I'll have positive slopes. So I know my solutions in here are going to look like this. Equilibrium, and then they're going to go positive, and then they can't cross that equilibrium there, so they're going to go like that. All right, and then let's see what happens up here. Pick a value bigger than 3. P larger than 3, then dp dt is going to be a positive, and then 3 minus p, if p is bigger than 3, will be a negative. So we'll have a negative. So slopes along here be negative, and so solutions are going to have negative slope, so they're going to come down like that. Okay, let's answer some questions based on that direction field. If the initial population is 4,000, that would be up here, then what can you say about the limiting population p of t as t goes to infinity? Well, the population, if you're starting up here at 4,000, it's eventually going to have to decrease to 3,000 because all the slopes are negative. It can't go up. It's going to have to come down, and it can't cross that line. If p of 0 is 2, what about the limiting population? So let's say we're starting out here. Well, we're going to have to go up and over, so the population is going to increase to 3,000. And then if the initial population is 1,000, can it ever increase to 5,000? So if you start down here, can you ever end up here? And no, if you start at 1,000, it cannot exceed 3,000. Okay,